Here I've created a very simple robot out of Lego. It's got simply one rotational joint or one revolute joint, and the end effector position of the robot can follow any point around a circle. It's not particularly interesting or particularly useful.
What you're interested in now is to describe the pose of the end effector of this one joint robot. The end effector is indicated by this symbol here. You will recall from an earlier lecture that when we want to describe the pose of an object in 2 dimensions, we attach a coordinate frame to it, and the position of the object is described by the position of the origin of the coordinate frame, and the orientation of the object is described by the angle between that coordinate frame and the reference coordinate frame. I've indicated here a reference coordinate frame with the axes x and y. And the first thing we're going to do is to rotate that coordinate frame by the angle Q1. That's the joint angle of our 1 degree of freedom robot. So I'm going to apply a homogeneous transformation, a rotation by the angle Q1. And now I'm going to translate the coordinate frame along the link of the robot. So I'm going to apply a translation in the x direction. So the grey coordinate frame shown here represents the pose of the robot. We get to the end effector coordinate frame by rotating and then translating the reference coordinate frame. All of these transforms are in 2 dimensions, so we say that they belong to the set SE2. That's the set of all translations and rotations in 2 dimensions. Using what we learnt in an earlier lecture, I can expand this out, and then I can multiply the 2 matrices together, and I come up with a single homogeneous transformation matrix which describes the pose of the end effector. The position of the end effector is given by these 2 elements in the homogeneous transformation matrix, and I've written them out here, and we can see that they describe a set of points which lie on a circle of radius A1. So the position of the end effector is a function of the joint angle Q1, and the orientation of the end effector, which is given by this matrix here, is also a function of Q1. So it's not possible for us to independently set the position and the orientation of the robot. There are just not enough joints or degrees of freedom in a simple robot like this. Let's look at doing this in MATLAB. I'm going to define a couple of workspace variables, A1 which represents the length of the first link, and Q1 which represents the joint angle. Now in order to determine the end effector pose, I need to multiply together a couple of elementary transformations. And an easy way to do this using the robotics toolbox is with the function called trchain2. It computes the result of a chain of homogeneous transformations. So the first one in the chain is a rotation by Q1, and that's followed by a translation in the x direction, that's along the link, by a distance A1. I just represent that as a string in MATLAB. And then I pass in the joint angle that I'm interested in, which is Q1. And here is the result. And what this has done is when the trchain2 function is executing, it looks for the variable A1 in the workspace, and it looks for the variable Q1 as being the first element of the vector that I passed in. So A1 from the workspace, Q1 comes from the passed vector. And here is, in numeric form, the 3x3 homogeneous transformation matrix representing the pose of the end effector of our simple one-link robot. Now, I can do it using symbols instead of numbers, and to do that I invoke some functions from MATLAB's symbolic toolbox, and I'm going to say that Q1 is a symbol and A1 is a symbol. Now what I'm going to do is just repeat the command that I did previously, and what we have here is a symbolic representation of the pose of the end effector. It's the same as we worked out a slide ago. Another thing I can do using the robotics toolbox is to import a model of a planar one joint robot, and I do that with this function MDL for model planar one, and we created a new variable in our workspace, variable called P1, and we can see it's of a serial link type. It's a robot manipulator type object. Now with this particular object, it's got a number of methods, and an interesting method is the teach method, And if I invoke that, what we see here is a graphical representation of a one-link robot and a simple teach pendant. There's a single slider here, and as I adjust the slider, we see the robot move. I'm adjusting the value of the first joint angle. What we see here is the XY coordinate of the end effector of the robot changing as I adjust its joint angle.